Okay, so I'm happy to introduce Tom Hutchcroft from the University of Cambridge, and he will be talking about power law bounds for critical long-range percolation.
Thanks. Thanks for inviting me. I'm glad to finally come. I'm sorry that we haven't overlapped with our other seminars because I can't come normally. So I'm going to be talking about long-range percolation. So let me just start by defining the model. Probably this is something many of you will have heard of before. So the way I'm going to set it up is we have the lattice ZD, and we're going to start with just the vertices of ZD and no edges, and then we're going to kind of drop edges randomly, some very long, onto this lattice in some kind of Poissonian way. So the way we do this is we take a function j from ZD to non-negative reals, and we're going to assume that this function is integrable, meaning if I sum it over all points, it's infinite, and symmetric, so j of minus x should be the same as j of x. Okay. Now, given such a function j, long-range percolation is the graph with vertex set zd, and where each possible edge, so each pair xy, is made into an edge with probability 1 minus e to the minus beta times j of y minus x. The precise function here isn't very important. The point is that this is between 0 and 1, so it makes sense, and it's roughly beta times j of y minus x when. Okay. So again, we start with no vertices and then we're adding these edges on, so there's no special roles for nearest neighbors. Although you could consider ordinary nearest neighbor percolation within this framework by taking j to be the indicator function that x is the neighbor of the origin. Okay, but we're not going to be interested in nearest neighbor percolation, but in genuinely long-range percolation. And we'll be most interested in the case that j kind of falls off like some power of the distance. And it's convenient to write the power in this way, where j of x is approximately the side of x to the minus d minus alpha, where alpha is positive. Okay. And the reason to write it this way is if the power is smaller than d, or if alpha is 0 or negative, if you like, then the function would not be integrable. Okay. Which is not to say that that regime is not interesting, it's just that it doesn't undergo a phase transition and you get edges of infinite degree and so on. So the questions would ask in that setting are different. Okay. So just as with ordinary nearest neighbor percolation, we have phase transitions. So if the dimension is at least 2, this happens no matter what the value of alpha is, just by comparison with ordinary nearest neighbor percolation. Whereas if d is if you're in one dimension, then you have a phase transition provided alpha is sufficiently small. So if alpha is less than 1. And you should think that the smaller alpha it is, the easier it is to have very long edges. Now, it might seem like perhaps this ought to be a more complicated model than nearest neighbor percolation, but it's actually better understood than nearest neighbor percolation in many ways. So in particular, it's a theorem of Noam Berger from 2002 that if alpha is less than d, then the phase transition is continuous, i.e. there are no infinite clusters at criticality. So I should say, by the way, that of course, the way this is set up with this factor of beta, that as we increase beta, we're increasing the density of edges. So just like in normal percolation, we get this phase transition where small beta, there are too few edges, there are no infinite clusters. For large enough beta, there's a unique infinite cluster. So yeah, so as I said, Berger proved that at least when alpha is sufficiently small, there are no infinite clusters at criticality. And this condition alpha less than d is actually best possible because in the one-dimensional case, at least, it's a theorem of Eisenman and Newman. Actually, this is something that was a new proof of on the archive fairly recently by Barban, Dumno-Kopan, some other people. Anyway, so but they proved that in one dimension, with alpha equal to 1, you actually get a discontinuous phase transition. So you get an infinite cluster emerging all at once from nowhere. And this example, just to mention, it's something that's important to understand if you'd like to prove things about percolation having a continuous phase transition in other settings, whatever you do needs to not apply to this example, right? So it's kind of a various proof strategies one might have. And again, this is very nice because this continuity of the phase transition result of Berger is something that something that holds in every dimension with actually a reasonably weak hypothesis, and it's totally unknown for neuroscience models. So just to give you some brief indication of why this condition alpha strictly less than D might be important. So it has a nice geometric characterization, which is that suppose you take two n by n or side length n boxes that are kind of macroscopically separated, so they have distance of order n as well. Okay. Then if you look at the number of edges that you put between those boxes, well, you can compute what it is in expectation, and you find that when alpha is less than D, this is going to be a large number of these long edges with high probability. When alpha is equal to D, it's going to be like an order 1 plus number of edges. Whereas when alpha is bigger than D, there will be no such long edges with high probability. So there's kind of these three regimes where the geometry of the model sort of changes. Berger's proof of his theorem, it basically works by saying, take some beta, assume you have an infinite cluster at that beta, and then prove that that infinite cluster itself has PC less than 1. So if you reduce the density of it, you still have an infinite cluster, i.e. this set where an infinite cluster exists is open. So this is nice, but it doesn't really tell you anything about critical percolation per se, because it's more studying the supercritical regime. Okay. So what I want to tell you about today is a new and completely different proof of Berger's theorem, which is quantitative and yields power law upper bounds on various things. So in particular, we get that the distribute. So this is the cluster at the origin. So the probability that the cluster at the origin contains at least n vertices is bounded by some power of n. And similarly, we also get a power law bound on point-to-point connection probabilities, at least when you average over a box. So the average point-to-point connection probability is bounded over a box of size R, is bounded by some number. Okay. So, of course, when I said that we want to look at J that decay roughly like a power, I didn't say exactly what I mean. So the precise conditions that go into this theorem are that J of x is at least some positive constant times the appropriate power of x, at least when x is sufficiently large. Okay, so we actually don't need very much regularity on these things. Now, this theorem is really most interesting when the dimension D is smaller than 6 and alpha is bigger than D over 3. And the reason why is that in the other case, when either the dimension is large or alpha is smaller than D over 3, we expect mean field critical behavior to hold. So, critical percolation, this is this high dimensional type regime where critical percolation should behave like critical branching and walk. And, all these exponents are known, and we kind of know how to prove this, at least under some stronger assumptions using in particular, in this high dimensional regime, we know that it should be n to the minus a half here. But this theorem also applies to some situations where you're below the upper critical dimension, so you should not have mean field behavior. And I think other than two-dimensional models, where obviously the attendees of the seminar know very well that there are many things you can do and many things that can be proven, I think this is the kind of first instance where we can prove some moral bounds for, let's say, a three-dimensional model that's not supposed to happen for the behavior. Okay. And the proof is actually very general, so the precise choice of lattice and things like that aren't important. Now, just to say a bit more about what's conjectured to happen. So, of course, again, people attending the seminar know very well that various things at criticality should be described by critical exponents in percolation, long-range percolation, or whatever. So we expect in particular that the tail of the volume at criticality should have some kind of power law distribution, which is the exponent is traditionally denoted 1 over delta. And we also expect that you have some power law fall off for the connection probabilities at criticality, which is normally written in this way. And again, under this high dimensionality condition, we know that delta should be 2 and eta should be 0, which is proven by this late expansion type stuff. By error inside. Whereas in lower dimensions we really expect the exponents to be different, and of course we understand the nearest neighbor models in 2 dimensions, at least some of them, and in between it's stereos. Okay, so if you take the results I wrote before and you interpret it in terms of these critical exponents, these are the bounds that you get. So to give you some more context, in the physics literature, there's actually a surprisingly simple prediction for how these exponents should behave. But first of all, let's suppose we're in 1 dimension. Okay? Then the prediction is that when you do long-range percolation, first of all, this 2 minus eta, which is describing this correction to the decay of the 2-point function, should always be given by alpha exactly. Okay, so this is an extremely simple prediction. And if you take this prediction and you do some standard heuristic scaling relation type arguments, you get the prediction that delta should be this kind of piecewise defined function where it's 2 in the mean field regime, and then it's 1 plus alpha with 1 minus. Okay. Now, okay, so that's 1 dimension, so maybe it's not surprising that it's so simple. But actually, the prediction in higher dimensions isn't that much more complicated. So basically, the prediction is that you have these kind of 2 regimes depending on the value of alpha, where when alpha is small, you're in this kind of long-range dominant regime where the model basically behaves the same way as the 1-dimensional model. So the long edges are really controlling everything, and actually the fact that you're arranged in a line or in a plane, whatever, is kind of irrelevant. And then when alpha is large enough, you have a short-range dominant regime where you expect the long-range model to behave in the same way as the nearest neighbor model. Essentially, what these predictions say is that these are kind of the only 2 possibilities. So more precisely, if you look at this exponent describing the 2-point function, it should just be the minimum of alpha with its value that it takes in the nearest neighbor model. Okay, so it's like this exponent is increasing, but somehow until it just hits the value that it has for the nearest neighbor model, which you can think of as like alpha equals infinity, and then it just stabilizes. Okay, and similarly, if you take these kind of scaling and hyperscaling type stuff, you can get a similar prediction for the value of the exponent delta. Okay, so this is really interesting. It's none of this stuff. There's actually not so much work on it really. And something I've been doing more recently since the work I'm telling you about is proving some of these things in a slightly simpler setting of hierarchical models, which is sort of like the 1-dimensional case, but even simpler. But anyway, these are really interesting predictions, and yeah, again, they're very simple, except that of course you don't know what these nearest neighbor So, and one more thing to say is that if you're very brave, you can try to understand what happens at this so-called crossover value of alpha, where the long-range dominant regime meets the short-range dominant regime. And there, these two effects are kind of balanced, and one of various logarithmic corrections, things like that. And this is actually something that's now understood in the high-dimensional case, at least, by Chen and Sakai. Okay. So just to compare the bounds that we obtain to these conjectural true values of the exponents, well, you can see in this graph for 2 and 3 dimensions. And basically, the upshot is that the exponent bounds we prove are kind of reasonable, but not very close. But maybe one thing I should mention is that, in particular, these physics predictions mean that the class of models that are treated by this theorem should actually include models that are in the same universality class as the nearest neighbour models in 3, 4, and 5 dimensions. But of course, proving that is not within the scope of these methods. Okay. But before telling you more about the proof of this theorem specifically, let's just talk quickly about how we might study critical percolation in general. Okay, so the way I like to think of this is there are kind of two main strategies that one might pursue. So one strategy, which I think is generally the most popular, is what I would call the supercritical strategy. So this is kind of like what Berger did, where you suppose for some p that you have an infinite cluster, and then you try to deduce things about the geometry of that cluster, and then try to deduce that that cluster itself has PC less than 1, so that if you reduce p a bit, you'd still have an infinite cluster, and therefore you won't have criticality. So there are many people have attacked the problem of critical percolation by that strategy. It tends not to produce quantitative results. Now, another thing you can try is what I call the subcritical strategy. So here, the idea is to study critical models by proving uniform bounds on subcritical models, and then deducing the critical models. So often the way this is done is using what's called a bootstrapping argument. So the idea is that you choose some bound that you know is going to hold when p is very small, say, and then you prove that this bound implies a strictly stronger version of itself. Okay? So that might seem like a strange thing to do, but if you can do that, then you actually deduce by continuity arguments that the strong form of the bound is going to hold uniformly on the whole subcritical phase. So an important example of this is in the Hara and Slade analysis of high-dimensional percolation by the Lace expansion, where, roughly speaking, what they do is they prove that in high enough dimensions, if p is less than pc, and you know that the probability x is connected to y is bounded by 3 times the Green's function for all x and y, then in fact it's bounded by twice the Green's function for x for all x and y. Okay. The actual bootstrapping used in the Lace expansion analysis of percolation is a bit more complicated than this, but this is essentially what they do. And if you can prove such an implication, again, you deduce via elementary continuity considerations that in fact this strong form of the bound has to hold uniformly all the way up to PC. Basically, because if you started violating the strong form of the bound, then when you've only just started violating it, you're still going to satisfy the weak form, but then you must satisfy the strong form. So, and of course, most of the work of Hara and Slade is to prove this implication. Okay. Now, the proof of the new theorem that I'm telling you about is also based on bootstrapping arguments, and it builds on ideas that were originally used to analyze percolation on some kind of in some non-Euclidean examples. So in particular, joint work with Jonathan Herman, where we looked at percolation on some groups of intermediate volume growth. So this is a nice example of some ideas that were developed to look at percolation in these kind of unusual geometric settings, eventually being useful to get new insights into Euclidean models. And one key idea going into the proof is what I call the two-ghost inequality. Where does this come from? Well, it's so in 1986, Eisenman, Keston, and Newman proved that there is at most one infinite cluster in supercritical percolation on ZD. Okay, and that they were the first to do it. Of course, Berkman and Keene came along 2 years later with a much simpler proof, which is the one most people learn now. But Eisenman, Keston, Newman were the first, and in fact, their proof, at least implicitly, contains stronger quantitative information than the Berkman-Keene proof. So in particular, what it tells you, and again, this is only really implicit in the paper, is that if you take an edge at the lattice and take a box with side length n, and look at the event that the endpoints of the edge are in distinct clusters, each of which reaches the boundary of the box. Okay? So what they proved essentially is that this probability of this event is always bounded by log n over root n times a constant. Okay? In fact, you don't even really need the log n. Okay. In some of my earlier work, which kind of started this program that led to the thing I'm talking about today, I proved a stronger and more general form of this Eisenman-Keston-Newman theorem. Which is what I call the two-ghost inequality. And the point is that it's a similar bound, but it works directly with volumes instead of radii. It's also more general, and it's stronger because volumes are bigger than radii, at least in the nearest neighbor case, and working with volumes just makes things much more appropriate looking at long-range models. Okay, and what it says is let's take 2 points, the origin and x, and we look at the event that the origin and x are both in clusters of size at least n, and at least one of these two clusters is finite. Okay, then what it says is that the probability, and that they're in distinct, these clusters are distinct, that if I sum over all vertices in the lattice, and I multiply by each one by this prefactor, which is roughly root beta and jx, then what I get is bounded by a constant over root n. Okay. Where this is like 1,000 hundreds things possible. So basically what this is telling you is that it's difficult a priori, without knowing really anything about percolation yet, it's always difficult to have two big clusters that are near each other, two distinct big clusters near each other. And the idea of the proof is going to be to try to leverage this fact that it's difficult to have two big clusters near each other and learn that it's actually difficult just to have one big cluster. So in particular, we'll use this two-ghost inequality together with an assumed volume tail bound to deduce a stronger volume tail bound, and then use this kind of bootstrapping idea. So what I want to show you now is a proof of a weaker theorem, which is going to apply, it's going to need a stronger assumption on alpha that is smaller than d over 4 instead of small d, and it's also going to give us a worse okay, but this is something I can completely show you all the details of. See how it works. So here's the idea. So we'll call this exponent theta. But so what we want to prove is there exists a constant c such that if beta is subcritical and not too small, then whenever I have a constant A such that this volume tail bound is satisfied, so the probability the cluster at the origin is bigger than n is bounded by A times n to the minus theta for all n, then in fact this stronger version of the same bound also holds where A is replaced by C times the square root of A plus 1. Okay, so let's see why, before proving this implication, let's see how we would use this to deduce that we get a bound like this in criticality. Well, for each beta less than beta c, let's define A of beta to be the best value of the constant such that this inequality holds for all n. Okay? Now, we know by sharpness of the phase transition that below beta c, the tail of the volume of the cluster at the origin actually is exponentially decaying. So in particular, this constant A of beta is certainly finite for every beta smaller than beta c. Okay, but if we apply this implication, what we learn is that A of beta is bounded by c times the square root of itself plus 1. Right? And because when beta is smaller than beta c, this is finite, we can safely rearrange this inequality. We learn that A of beta is bounded by some constant that doesn't depend on beta, and therefore, by continuity, we get the same bound holding as well. Okay. So hopefully that's clear. That you see, it's pretty, the actual bootstrapping part, once you prove an implication like this, it's very simple to deduce that the strong form of the bound is going to hold uniformly by continuity. Okay, so now, of course, we have to prove that this implication holds. Okay, so let's define lambda r to be the box of minus r and r. Okay, and let's fix beta in this range, but we're not going to allow any constants that appear to depend on beta. And let's assume that this bound holds, and again, we want to deduce that the stronger form of the same bound holds. So for each vertex x and n, let's define Sxn to be this event that I get some control of from the two-ghost inequality, that the origin and x are both in large clusters, distinct large clusters. Okay. So in particular, the two-ghost inequality tells us that, well, it really gave us a bound over this sum with these j of x prefactors. Right? If we sum these probabilities over a box, then we know by assumption that these prefactors aren't too small. So we can pull them out, and we get that the sum over the box is bounded by r to the d plus alpha, and the sum with the prefactors. And then we use the two-ghost inequality, we get a factor of 1 over root n. And by the way, I should have said, r here is a parameter that we're going to optimize over later. Okay. Now, on the other hand, we can lower bound the same probability, because this is the event that the origin and x are both in large clusters that are distinct. So we can bound that from below by the probability that the origin and x are both in large clusters minus the probability that they're connected to each other. And then we can use, positive association FKG inequality to bound this first probability by the square of the probability that the origin is in a large cluster. And if you rearrange that, you get this inequality. So the idea is going to be to use this to get a better bound on the left-hand side than we started with. So if we average this inequality over the box, we get that the probability that the origin is in a cluster of size at least n squared is bounded by this average connection probability plus this average two big clusters probability. Okay. So the second one we already saw how to bound. The first one, we can give a crude bound as follows. So if we sum this connection probabilities over the box, that's the same thing as the expected size of the cluster, the intersection of the cluster at the origin with the box, which of course I can bound that by the expectation of the minimum of the cluster at the origin with the total size of the box, right? And then I can write this expectation as a sum of tail probabilities in the usual way, And using our assumption that we started with on these, bound this by a n to the minus theta. I do my usual calculus assigning powers, and I get it bounded this form. So if we put these two things together, so this bound on the sum of the connection probabilities and this bound on the sum of these two bit cluster probabilities, we get this. Okay, and now we optimize over R, and I'm not going to go through the arithmetic because it would be too tedious, but you choose R to be appropriately chosen power of n, and you find that the right hand side is bounded by C a plus 1 n to the minus 2 theta, okay, which is exactly what we needed, right? Because now we just take square roots of both sides. And of course, how did I arrive at this value of theta here? Well, I just got to this stage of the argument with theta indeterminate, and then I chose the value of theta that made this work. So you can see this proof is actually very simple. Of course, it is quite a lot weaker than we'd like. In particular, this condition on alpha having to be smaller than d over 4 is much weaker than we'd like. So there are two main ingredients that go into improving this and proving the full strength version of the theorem. So one of them is just to prove a slightly stronger version of the two-ghost inequality that handles very long edges a bit better. Okay. There's a statement here, but seeing I didn't tell you about the proof of the original version, I'm not going to tell you about the proof of this improvement either. So the more interesting additional ingredient that goes into the full strength theorem is that we want to find a better way of converting volume tail bounds into connection probability bounds, aka two-point function bounds. Okay. So in this proof that I just showed you, we use this very naive way of doing this, where in particular this inequality here is extremely wasteful, right? Bounding the size of the intersection by the minimum. Okay. So we'd like to do this more efficiently, and this is what I'm going to talk about. In fact, the things that I'm going to talk about now about efficiently turning volume tail bounds into two-point function bounds, this isn't really anything particular to long-range percolation. This is going to give us some interesting new things for nearest neighbour models as well. So in light of that, I want to consider things at a higher level of generality before. So from now on, let's look at weighted graphs. So these are just graphs in the usual sense, together with a weight function j, which sends edges to non-negative numbers. Okay, so obviously ordinary graphs like the lattices are weighted graphs where you just take all the edges to be 1, if you like, and the long-range models as we've been considering them so far, you can consider the graph that has vertex set z, edge set equal to all pairs of points, and j defined as before. Okay. So this weighted graph setup basically lets us consider both short and long-range models in any unified framework. Okay. Now this thing that I'm going to tell you about, so we want to find a more efficient way of converting volume tail bounds into connection probability bounds. And this is going to go through something else about maximum cluster sizes in finite regions. So let's suppose we have our weighted graph. So I think a good example to keep in mind from now on is just ordinary nearest neighbor percolation on ZD. Okay. And suppose I give you a finite set of vertices in this graph, lambda. Okay. So I define this quantity, this random variable k max of lambda, to be the maximum intersection of a cluster in the graph with the set lambda. So you can imagine maybe lambda is a box, in ZD and I'm doing percolation on ZD, I look over all clusters, I find the one that has biggest intersection with lambda, that's this random variable. Okay, and I define this quantity here, m beta of lambda, to be essentially the median of this random variable. It's notationally convenient to define it using 1 over e instead of a half, but it's basically the median. So it's the minimum n where this tail probability is bounded by 1 over e. Okay, so it's kind of a typical value of this. So the theorem, which I'll later tell you how it's related to this thing about efficient conversion of volume tail bounds into two-point function bounds. What it says is that totally universally over all possible weighted graphs, all p, whatever, this random variable is always tight. So it's always of the same order as its median with high probability. Okay, obviously that's not the same as it being concentrated. It's like more like the log of the random variable. Okay, so it's very unlikely to be much larger or much smaller than its typical order. Okay, so in particular, what the theorem says is that if you take any weighted graph you like, any finite set, the probability this one variable is more than alpha times its typical value is always exponentially small in alpha, specific universal constants, and similarly, probability that it's smaller than its typical value by a factor of epsilon is linearly small. Okay. Moreover, if you take a specific vertex and you say what's the probability that that vertex has a cluster that has a big intersection with lambda that's bigger than the typical value by a factor of alpha, then this is bounded by this exponential term multiplied by the probability that this this specific cluster has intersection of this size. Okay. This theorem is an analytic consequence, basically, of this more basic version of the same theorem, which says that if you have any number lambda, small, then the probability this random variable is bigger than 3 to the k times lambda is at most the probability that it's at least lambda to the power 3 to the k minus 1 plus 1. And similarly, this version where you have specific vertex. Okay, so you get the probability that the maximum cluster is bigger than lambda 3 to the 3 to the k minus 1 times the probability that this specific cluster is large. Okay. And of course, I should say, another example to keep in mind is the case that G is finite and lambda is the entire vertex. Okay. So in that case, for example, maybe you do percolation on a torus or something like that. It's saying that the largest cluster in percolation on the torus is always of the same order as its median with high. So before telling you about the proof of this, let's see why it's relevant to what I was telling you about before. So first of all, let's suppose that we have our weighted graph, whatever, and that we know that the probability that a cluster has large size is bounded by this power law. Okay. Then what this tells us is that if we take a finite set of vertices lambda, then the probability that the intersection of the cluster with lambda is bigger than n is bounded by this thing, where basically I have this power law term that I get from the assumption, but I gain this kind of exponential dampening term that says it's hard for this to be much larger than the typical value of the maximum. And this is useful because it's exactly what lets you get these efficient conversion of volume tail bounds into two-point function bounds. So in particular, what you can prove is if you assume this power law bound on the volume tail, and you take any finite set of vertices lambda, then first of all, this typical value of the maximum cluster is bounded by this power of lambda to the 1 over 1 plus theta to the side of the loop. And similarly, the average connection probability between two vertices is bounded by, again, another power of the size of lambda. And this is nice, and it's actually, these bounds are expected to be sharp on, if you do percolation on the torus in any dimension, and you take lambda to be the whole torus, this should be sharp in every dimension. So if you had the right up bound on the volume tail, you should use the right order for the maximum cluster size and the two-form function. So one way to think of this is that it gives you a rigorous hyperscaling inequality. So that these exponents eta and delta that we defined before via this related via this inequality. Again, this is expected to be in equality in low dimensions and a strict inequality in high dimensions. So let's see the deduction of this corollary from the theorem, because it's very simple. So first of all, if I fix a vertex u in lambda and sum over all other vertices v in lambda as a connection probability, well, again, that's just the same thing as the expected size of the intersection of the cluster with lambda. And again, I can write this in the usual way as a sum of tail probabilities, and using this assumption together with what I just told you about how you gain this exponential dampening term when you try and go above the maximum, what you learn is that this sum is bounded by a constant times m to the 1 minus theta. Okay? But on the other hand, you can also bound this from below, at least if you sum over pairs of vertices, then the sum of the connection probabilities is equal to the expected number of pairs of vertices that are connected to each other. And of course, that's at least the expectation of the square of this maximum cluster size, which by definition, this typical value is at least a constant times n squared. Okay, so if you just compare these two inequalities, you deduce everything that I just told you in this problem. So in the last few minutes, let me just say something about how this universal tightness theorem is proven. So let's just quickly look at the statement again. So we're going to prove this more basic version. And so we want to prove that it's, having a cluster of size at least 3 to the k times lambda, the probability bounded by the maximum cluster size being at least lambda to this power of 3 to the k minus 1 plus 1. Okay, and the way we're going to do this is using the BK inequality together with a combinatorial. So let me show you this in a different order to how I wrote it. Okay, so so what does the BK inequality say? I imagine this will be familiar to you. So suppose we have two increasing events, A and B, for percolation. Okay, so I say that a set of edges is a witness for the event A if those edges are all open, and just knowing that those edges are open guarantees that the event A must occur. So for example, A might be the event that X is connected to Y, then any open path between X and Y would be a witness for the event A. Okay? This event A circle B, which is called the disjoint occurrence of A and B, is defined to be the event that A and B both occur, and there's a witness for A and a witness for B that are disjoint from each other. Okay? And similarly, you can define this with multiple events. Okay? And the BK inequality says that the probability of a disjoint occurrence of n increasing events is bounded by the product of the probability of the events. Okay. So in order to prove this universal tightness theorem, it suffices to prove the following deterministic facts, which is just an inclusion of sets, that this event that the maximum cluster size has size at least 3 to the k times lambda is included in the disjoint occurrence of 3 to the k minus 1 plus 1 copies of the event that the maximum cluster size is least lambda. Okay? And similarly with this version where you have a specific vertex, you get the disjoint occurrence where you have one copy of the event that cluster is large, and 3 to the k-1 copies of the event that the maximum cluster size is large. Okay, so if we can prove this deterministic inclusion of events, then we're done by the BK inequality. Okay. And the way you prove this is, so this is going to follow by following general combinatorial lemma. So let's take G to be any connected locally finite graph, and let's take A to be a finite subset of the vertex set with at least 3 elements. Okay. And the claim is that in this situation, I can find 2 disjoint sets of edges inside the edge set, each of which spans a connected subgraph of the big graph. Okay, so if I take the subgraph that has exactly those edges and only those vertices that are incident to those edges get something connected, and that the sets, the 2 sets of vertices that are incident to the set E1 and E2 both intersect A in a kind of by this kind of moderate amount. So between the set has between 1/3 and 2/3 of the total volume of A. Okay, and the way we'll apply this is we'll take G to be the cluster which attains this maximum in the definition of the largest cluster, and we'll take A to be the intersection of this cluster with lambda. Okay. And the proof of this is simple. Maybe before saying anything about that, what we do is once you have this way of splitting a graph into 2 sets, you can apply it iteratively. So you can learn that if you have a set, if A is now of size at least 3 to the k, then you can find a set of at least 3 to the k-1 plus 1 disjoint sets of edges in your graph, each of which spans a connected subgraph of G, and which all have, if you look at the set of incident vertices, its intersection with A will be between A over 3 to k and A over 3 to k-1. Okay? And you know, the way you deduce this iterative version from the splitting into 2 sets version, well, you just split into 2 sets, and then if one of the sets is still too big, you split it again, and you keep splitting each set that's too big into 2 pieces until you've got all these small pieces. Okay. And if you apply this, again, you take the graph to be the biggest cluster, and you take A to be the intersection of the cluster with lambda, then these m sets that you get are exactly the m disjoint witnesses for the event that the maximum cluster is large. Okay. So perhaps I should end now if I'm out of time. Otherwise, I'm happy to tell you about the proof of this combinatorial lemma.
Maybe finish the proof.
Yeah, I think that's fine. Yeah.
Okay, good. It shouldn't take too long. So again, what we want to do is split the edge set into 2 disjoint sets that both have span connected subgraphs, and they have a good intersection with the with this set A. Okay, so we can always consider the case that the graph is a tree, because if not, let's just start by taking a spanning tree. And in this case, we'll take these 2 sets to form a partition of the edge set of the tree. So here's what we do. Let's root key an element of A. Okay. And then what we'll do is recursively construct a sequence of edges where we start with the empty sets, and then at each intermediate step, so between the first one where it's empty and the last one where it's going to be the whole vertex set, we're going to have a strict subset, which has the property that both EI and its complement span connected subgraphs of the tree. Okay. And at each time, so we'll have a distinguished vertex, which we start as being the root, and then at each subsequent time, it's going to be the unique vertex that's incident to both EI and its complement. Okay. And basically what we want to try to do is kind of, it's like the opposite of a greedy algorithm. We want to grow this set EI while maintaining this property that both it and its complement are connected, but while eating up as little of A as we can at each step. Okay. And so here's how we do this. So we have this vertex VI, which is, again, it's the boundary between the unique vertex that's the boundary of EI and its complement. Okay. Now there are two settings. Either VI has exactly one child, and in that case, i.e. One child, sorry, not incident, not included in the edges we've already taken in EI. And in that case, what we do is we just add the edge to that child into our set EI plus 1, and then that child is going to become our new boundary vertex. Okay? Otherwise, this boundary vertex has at least two children which are not incident to EI. Okay, so what we do in that case is we pick the child that has the fewest elements of A descended from it, and then we form EI plus 1 by adding in all the edges in this subtree that's descended from that vertex. Okay. So it's hopefully clear by induction that this is going to have this property that EI and its complements are always connected. Okay. So I need to just walk you through this example quickly. Okay, so let's say we have this tree, and the red circled vertices are the elements of A. Then we start with this root. Okay, so the root has three children, so we're in the second setting, where we want to pick one of the children that has the fewest elements of A in its the descent from it. Okay, so maybe let's say we take this one on the right. And then we're going to add, to form E1, we're going to add all these edges in that are descended from this child. Okay, so then we get E1, and then at the next step, again, we now have two children, so we're still in the second setting. This one has fewer descendants that belong to A, just one, so we add that in. Okay, and now we're in the setting where we only have one child, so we add this guy in. Now this guy is the boundary vertex. It has two children. This one has 0 descendants in A, so we pick that. And do this, and this, and this. Okay. Again, we're kind of growing the set, maintaining the property that both it and its complement are connected, but trying to eat up as little of A as possible at each step. And basically, it's not very hard to see, and I'll skip the details, that the first time you get at least a third of A, you don't yet have 2/3 of A. Because of this way, you're defining it where you're eating up as little of A as you can at each step. Okay, so if you look at that first time that you've included at least a third of A in this set of instant vertices, the partition that you have at that time is going to be exactly what you want. Okay, so that's the proof. I'll end there and be to take any questions.